Okay, Assalamualaikum to the Muslim and a very good morning to all of you. So welcome again to our physics class for today, Wednesday, August of 8th, 2021. Okay, so for those who would like to join me in my studio, you can click on this StreamYard link. Okay, you can prepare with your mic and camera so I can add you into the studio. So for those who are not able to join, you can follow me from the live chat. Okay, so I am conducting our class today live stream on YouTube. So for those who cannot able to join the Google Meet, so I hope later you can watch back this video so you won't miss any part of the lesson. Okay, this is one effort to help those who have problem with the Google Meet or with the data, because once you watch in YouTube, you will use less data compare if you follow from Google Meet. Okay, are you ready, students? So I have placed an exercises on PDF file in your Telegram group, so you can check from there before we begin. Okay. So we will continue today with chapter 4, gas law, the third and final law, which is Boyle's law. Which is pressure law. Okay, earlier we have discussed Boyle's law. You also already know what is kinetic theory of gas, and you also have studied what is Charles' law. Remember, students, Boyle's law relates pressure and volume at constant temperature. Okay, and then in Charles' law, we learn that volume of gas are directly proportional to the absolute temperature at a constant pressure. Okay, and then for today, we will continue with the third law, which is called as Gay-Lussac law, or also known as pressure law. All right. So you can get ready with your module. This module I have gave you earlier before. So for those who have print out, you can refer to them. For those who are not print out, no problem. You just focus on my screen first. Okay. So we do some recaps on Boyle's law. Kita buat dulu sedikit ulang kaji. Okay. If you still remember, what do we learn before in Boyle's law? It stated that pressure is inversely proportional to the volume, okay, of gas for a fixed mass of gas at constant temperature. Okay, why according to this triangle, when temperature is constant, so we close the temperature, you can see that pressure inversely proportional to volume. Okay, and this is the formula for Boyle's law. P1 V1 equal P2 V2. Okay. And then according to kinetic theory of matter, how do we explain Boyle's law? So what happened? You can see what happened into these two cylinders. Cylinder on the left, it has a greater volume, right? And the pressure here is lower. Why the pressure here is lower? Because the rate of collision between the molecule and the inner wall of the container is lower. So pressure produced will be lower. And then what happened when we lower down this piston? So the space become narrow. Okay, the space become narrow means the volume is now decreases. So the particle is closer to one and another. So they will collide with the inner wall of the container more frequent. Okay, more frequent collision mean produce higher pressure. Okay, because of the rate collision increases, so force acting on the wall increases. So that means pressure exerted increases. Okay, so this is Boyle's law according to kinetic theory of gas. Okay, we have 50 students now. Okay, for those monitor, please call your friend to join this lesson. Okay, now let's check on our third learning. Ini sudah kan? Ini sudah belajar, right? Okay, so I think nanti cikgu tunjuk. I supposed to begin with slide number 19. Sorry, sini. Okay. So today we will continue with the fourth learning standard. Okay, doing experiment to determine the relationship between pressure and temperature of a fixed mass gas at constant volume. So this is what pressure law about, or also known as Gay-Lussac law. Okay, so let's check at these two diagrams first as our induction set. Okay, look at photograph 4.6. Actually, you can find this in your textbook. Okay, it shows that air pressure in the tire of a car being measured on a hot day. Okay, the driver of the car touched the tire after the journey and found that the tire is hotter than before the journey. Means the temperature of the tire increases after a long journey. Okay, and then photograph 4.7 show the reading of the pressure gauge before and after the journey. So before the journey, the pressure reading is about 200. Okay, it's about 200. And after the journey, the pressure increases greater than 200, as you can see here. So it proves that the pressure increases when the temperature of the tire increases after a long journey. Okay. So this activity 5 is to tell us how to determine relationship between pressure and temperature. So how to know how does pressure relates to temperature at constant volume. Okay, if you look at diagram on the left and on the right, okay, the container have the same volume. Okay, the size of the container or the volume does not change. Okay, you tengok dekat sini. So what happened on the left side? What happened here? Okay, ini you tengok ini arrow ini low velocity. Long arrow itu show the liquid, the gas molecule moving at high velocity. So what happened when the temperature increases? Okay, it has a fixed volume. Now we increase the temperature. So you can see that the gas molecule moving in a higher velocity. Okay, why they are moving in a higher velocity? Can someone respond? Why when we increase the temperature, the gas molecule moving at higher velocity? Okay, can you type on the live chat? What is the reason? Temperature increase, gas molecule moving at high velocity. This is because when temperature increases, the kinetic energy of the molecule increases. So when the kinetic energy molecule increases, so they will move with a higher velocity. So what happened to the rate of collision? Rate of collision between the gas molecule and the inner wall of the container will increases, which means more forces acting on the wall, which is more pressure will be exerted. Very good, Nicholas. Okay, increase, say. Okay, then, so how to explain what happened to the gas molecule when heated? As I say, they receive kinetic energy. Okay, the kinetic energy of the gas molecule increases. They will move faster. Faster mean at high velocity and collide more frequent with the inner wall of the container. So this causes the pressure inside to be increases. Yes, very good. Okay. Ini apa jadi pada gas pressure? Increase. Okay, why? Because of the increasing in the rate of collision. Okay, then how to say about the relationship between gas pressure and temperature when the volume is constant? So from this, what can we say about the relationship between pressure and temperature? So how to write? You can say temperature increase, pressure increase. When temperature higher, pressure also higher. Or you can say directly proportional. Okay, accepted. Okay, the example, the simulation is shown here. Cool gas, low temperature, hot gas at high temperature, pressure is higher. Okay, yes, directly proportional is accepted. Okay. Okay, then let's check on the next slide. Okay, this is experiment 4.6 conducted again to study the relationship between pressure and temperature at constant volume. Okay, so the inference is temperature influence pressure. Okay, temperature affects pressure. So this is the hypothesis. The higher the temperature, the higher the pressure of the gas. Temperature is the manipulated variable. Okay, while pressure is the responding variable. So our fixed variable here is supposed to be volume. Okay, volume and mass of gas. Okay, so this is our variable, temperature, theta, responding variable is pressure, symbol is P, constant variable is the volume with the symbol V. Okay, so this is the setup of apparatus when we are studying pressure law. Okay, exact law. Okay, this is the flask containing air or gas inside. We immerse it in a beaker containing water, and then we supply heat to the beaker. And this part, the end of the flask, is connected to a delivery tube connected to a pressure gauge. So we can see the changes of the pressure reading when the temperature of the beaker increases. So you will see that when temperature is getting higher, the pointer of the pressure gauge also show higher reading. All right. This is all the material required. Okay, this is how we conduct the experiment. Set up, heat the water slowly, stir continuously. Why we need to stir? To make sure the heat supply even and uniform into all parts of the beaker, okay, until it reaches 30 degrees Celsius. Okay, so we record the reading and then we repeat the experiment with different temperature of 40, 50, 60, 70, and 80. And then we record our data in a table. Okay, let's say this is the data we collect, okay, at this temperature from 30 up to 80 degrees Celsius. So you can see that the air pressure is keep increasing. At 30 degree is 111. At 80 degree is the highest at 130 kilopascal. Okay. So what do we get from this data when you plot a graph? When you plot a graph from the table, this is what the graph looks like. A graph of pressure in kilopascal against temperature in degree Celsius. Okay. And if you extrapolate this graph, kalau you sambung, if you extrapolate this graph, where will it, when dia akan pergi sampai mana? What will be the reading of the temperature when the pressure is zero? Anybody knows? If we extrapolate this graph, we extend the line to the left until pressure is zero. So what is the temperature you will reach there? Can someone tell? Yeah, absolute zero. Absolute zero, what is the temperature? Negative 273 degrees Celsius. Yes, negative 273 degrees Celsius. The decimal places itu you can neglect. Okay, negative 273 degrees Celsius. Okay, so that is called as absolute zero. Remember we discussed about absolute zero before. What is absolute zero refers to, students? What is absolute zero refers to? What happened at negative 273 degrees Celsius? What happened to the gas molecule at negative 273 degrees Celsius? Gas molecule is at stationary. They are not moving. Okay, there are no activity. So they don't fill up spaces, which means volume is zero. So pressure also zero. Okay, so that is what happened at absolute temperature of negative 273 degrees Celsius, or also equal to 0 Kelvin. Volume is zero. Okay, volume zero, pressure also zero. Why? Because at that temperature, gas molecules are not moving. They are stationary. So not moving means no velocity. So no force applied to the wall, no pressure exerted on the wall of the container. All right. So I hope you're clear with that. So from here, what can we say about the pressure and temperature in degrees Celsius? So you can say the pressure of the air increases when temperature of the air increases. Yeah, stationary. Okay, volume zero, pressure also zero. Yes, very good. Okay. Okay, next. Let's check on the next part. Okay, this is the discussion we made from this activity. What is the advantage of using round bottom flask to heat the air? Okay, why in this experiment use the round bottom flask? It provides large volume. Okay, the reason is because it provides large volume and mass of air, so we can see a larger change of pressure in the experiment. Okay, and then second, the thermometer is placed in the large beaker filled with water. What is the assumption made so that the thermometer reading is the same as the temperature of the air in the round bottom flask? So what assumption we made here? Heat up even to all part. Okay, ini why we stir. This is the reason why we need to stir. Okay, when we are conducting the experiment. So heat up even to all part. So the heat distribute in all direction of the water. Okay, ini dia kata thermometer. What is the assumption made? So the thermometer reading is the same. The keyword is thermometer reading is the same as the temperature of the air in the round bottom flask. So there is a thermal contact, right? So we assume that thermal equilibrium is achieved. Okay, thermal equilibrium is achieved between the air in the flask and the water around it. Therefore, the reading of the thermometer shows the temperature of the air in the flask. So whatever the temperature of the water is similar to the temperature of the gas inside the round bottom flask. Are you clear with that, student number 2? Okay. Okay, then this is the graph shows pressure low. Okay, the sec low. So we have two type of graph here. The first graph, graph P against theta. It shows pressure of gas increase linearly with temperature. Okay, this is show the linear graph. Okay, pressure increase linearly with temperature in theta. It does not started from the origin. It is a straight line graph, not started from the origin. So we say pressure increase linearly with temperature in theta. Okay. While on the second graph, what can you see? The second graph is a graph of pressure against temperature in Kelvin. It is a straight line graph started from the origin. So this is what we call as a directly proportional graph. Okay. So this is what I say just now, what happened at absolute zero, at 0 degrees Celsius here. Okay, 0 degrees Celsius. Okay, ini 0 degrees Celsius. There's still a pressure, right? There is still a pressure means the gas is still moving at 0 degrees Celsius. The gas still moving. It occupies spaces. It produces pressure due to the collision of the gas molecule and the inner wall. But what happened when the temperature dropped to negative 273 degrees Celsius? What happened now? Pressure is zero. Okay, so pressure zero, you can read here, gas molecule no longer move, do not collide with the wall of the container, hence the pressure of the gas become zero. Okay, if I magnify my screen, you can see here. At 0 degrees Celsius, there's still a pressure. Mean there is a gas activity. It is moving. It exerts pressure on the inner wall. But now the temperature dropped to negative 273. You can see now pressure is zero. Mean no movement, no velocity, no force acting on the inner wall, so no pressure produced inside the container. Okay. So the second graph, we say graph P against T of gas in a straight line through the origin, where gas pressure directly proportional to the absolute temperature. Okay, 0 Kelvin is also known as absolute temperature. Okay, 0 Kelvin ini absolute temperature, and also similar to or equal to negative 273 degree Celsius. Okay, are you clear with that? Okay, so how do we write pressure law, or also known as Gay-Lussac law? Pressure is directly proportional. Pressure directly proportional to absolute temperature or absolute zero of a fixed mass of gas at constant volume. Okay, so if you write the definition for Boyle's, for Charles, or for Gay-Lussac law, it must be in a complete statement. Okay, first you write the relationship between the two variable. Pressure for Gay-Lussac, pressure directly proportional to absolute temperature. Fixed mass of gas, and what is the constant variable? Constant volume. Okay, if you just say pressure directly proportional to absolute temperature, 0 mark for definition. Okay, it must come in complete statement. Okay, and this is how we look at this triangle. So we close the V as the volume is constant, so P directly proportional to temperature. So the formula is P1 divide T1 equal P2 divide T2. Okay, try this question number 1. We have nitrogen gas in a light bulb at 60 kilopascal at initial temperature of 20 degrees Celsius. You have to calculate the temperature of the gas when the pressure inside the bulb rises to 90 kilopascal after the bulb light up. Okay, find the final temperature of the gas, student. Okay, I give you a guidance. This is how to convert, okay, temperature from degree Celsius into Kelvin. And below is to do the other round, to convert Kelvin into degree Celsius. Remember, when we are dealing with gas law, when you do the calculation, the temperature must always be in a unit of degree Celsius or in a unit of Kelvin. Anyone? When you deal with calculation involving gas law, okay, either Charles law or Gay-Lussac law, the temperature must be in degrees Celsius or must be in Kelvin. Which one? Which unit we apply? It must be in Kelvin. Okay, so the temperature are given in degrees Celsius, mean you have to convert into Kelvin. How to convert into Kelvin? By adding 273. Okay, by adding 273. So the initial temperature 20 degrees Celsius mean 293 Kelvin. Yes, Sinway, it is in Kelvin. So final temperature. So final temperature we are looking for. So what is the information that we have? So this is the equation we apply. P1 divide T1 equal P2 divide T2. So we do the substitution. P1 60 kilopascal, T1 293 Kelvin. Okay, and this is P2. Okay, the final pressure is 90 kilopascal. The unit is the same, both in kilopascal. So you don't have to write 90,000 in Pascal. Okay, no need because they are same unit. So you just write 60. Here is 90. Okay, then we are looking for this T2. So what is T2? Can you calculate value for T2? The final temperature of the nitrogen gas in the light bulb? It's supposed to be 439.5 Kelvin. Okay, 439.5 Kelvin. And if they ask you to convert into degrees Celsius, let's say this is an objective question and the final answer is placed in degrees Celsius, so you can convert back by minus 439.5 with 273. So we'll give you 166.5 degree Celsius. Okay, are you clear with that? This is a very basic, a very straightforward, a very simple question on pressure law. Okay, so we proceed with the next question. Okay, this is a structure question. You can see there is a car start a long journey from Malacca to Kedah through North-South Highway. The first question, why the car tire become hot after a long journey? Students, why the temperature of the tire increases? That is the meaning of this question. Why the car tire become hot after a long journey? Yeah, as long as you deal with gas law, the temperature must be in Kelvin when you do the calculation. Okay? Friction. Very good, Nicholas. It is due to friction. Frictional force between the tire and the surface of the road. Very good. This is what causes the temperature or the tire become hot due to friction. Okay, second, you tell friction also can get 1 mark. Okay, you just write friction, accepted. What will happen to the air pressure inside the tire? So what can you say about the pressure now? Okay, what can you say about the pressure? It should be, yes, very good. It should be increases. Okay, the pressure increases. And then what's next? What is the negative impact that will occur? Okay, when the pressure of the tire is getting increases, and increases, what might happen to the tire? What is the negative impact that will or might occur? Can you think? If the pressure of the tire is getting increases, yes, it can burst, Nicholas. Very simple. Okay. Dia boleh meletup. Okay, the tire can be burst. The high pressure may cause the tire to explode or to burst. Okay, explode or to burst. So what is the benefit for a driver to stop at the rest area? Okay, so the driver should enter the RNR. Okay, the rest area. What is the benefit of stopping at the rest area when you make a long journey? What is the reason? Okay, to cool down the tire. So to reduce its temperature. Yes, to let the tire cool down. I see that only Nicholas and Sinway are responding. Where are the rest? Are you there? Please respond actively in this lesson. Okay, you can write your idea. If it's wrong, no problem. We will be here to correct you. Okay, I will be here to correct you. So to cool down the tire, hence to reduce its pressure. Okay, simple application. Okay, so what's next? Okay, what's next? Okay, this is a very common. Okay, sometimes you are using this aerosol can. Explain why it is very dangerous to throw an empty aerosol can into fire, and name the gas law involved. Normally, when you read, there is a label written there. Do not throw into fire. Okay, you normally read this a label or a warning label on an aerosol can. Why? Okay, why, students? Explain why very dangerous to throw an empty aerosol can in a fire. Okay, this is example of essay question which allocate 4 marks. 4 marks. And then you have to state the gas law involved. So how can we begin our explanation? Any answer? Yes, the law is Gay-Lussac law. Wrong spelling there, Nicholas. Lussac, L-U-S-S-A-C. And please write G and L with the capital letter in the exam. Okay? How to explain this, students? So what happened when you throw into fire, when this can is heated, when the aerosol can is heated, mean when you throw it into fire, what happened? The temperature of the gas inside increases. Okay? So this is what first thing happened. When you throw it into fire, or heated, the temperature of the gas increases. Okay, then what happened next? What happened to the pressure? So when temperature increases, it means the rate of collision between gas molecule with the inner wall of the container increase. Okay, this is the second. Okay, Nicholas, write the answer there. It is because when the gas inside the can is being heated up, will cause high rate of collision, finally will explode. Okay, you can get 2 marks from this answer. Okay, 2 marks. First point, temperature increase. Second point, rate of collision with the inner wall of the container increases. So where to get another 2 marks? Another 2 marks, then gas pressure increase. This is the third mark. Okay, when the rate of collision between gas molecule with the inner wall increases, it means that the pressure inside the tin, inside the can increase. Okay, gas pressure increase. So I highlight the keyword can, heated, temperature increase. Okay, second point, rate of collision between gas molecule and inner wall increase. Okay, and for the third point, gas pressure increase. So this will cause the tin to be explode. Okay, and what is the law? Pressure law, or you can say Gay-Lussac law. Okay, so this is how you can find 4 marks from this question. Okay, so each point you write separately. You can use number also, number 1, number 2, number 3, number 4, and so on. Okay, are you clear with this question, students? Okay, so that's all for this slide. Pressure of gas law. Okay, so now let us try to do a few exercises on chapter 4. Okay, so we conclude this chapter with some practices. Okay, practice on certain SPM format paper. Okay, are you ready with the exercises? This one I have put in your Telegram group earlier, so you can check from there. For those who have printer at home, later you can print out. Okay, so let's try this question together. So what do we have? First, we try paper 2, section A. So in section A, altogether, there are 8 structured questions. Okay, so what are the example? Okay, this is example of question 6.1 and 6.2. They give you a diagram. Show an experiment carried out to investigate law of gas. A column of air is trapped in the capillary tube as it is heated for a period of time. So I magnified the diagram for you so you can see. This is the setup. You can see there is an air trap inside this capillary tube. Okay, and also at the other side, what happened when we supply heat, you can see that the column of air trap is increases. Okay, the sulfuric acid rise up, so the length of the air trap increases. Okay, so the first question, student, what is meant by heat? What is meant by heat? This is the basic question on heat. What is meant by heat? Anyone? What is meant by heat? It is energy. Yes, very good. It is a form of energy. You write the energy also enough. Okay, a form of energy. Energy itself will give you 1 mark. Okay, energy with affect by temperature. Okay, a form of energy. Okay, then second question, B1, you have to compare. Compare the length of air trap in the capillary tube in diagram 6.1 and 6.2. So how we compare the length of air trap? Okay, this is the length of the air trap in diagram 6.1 and this is the length of the air trap in diagram 6.2. So how to write the comparison? This is Malacca trial 2008. So how we do the comparison? You can say that, yes, 6.2 greater than 6.1. Okay, 6.2 bigger than 6.1 or the other way around. 6.1 lower than 6.2. Here, you can use the mathematical expression, no problem. Okay, you can use the mathematical expression as well. Okay, 6.2 greater than 6.1 or vice versa. 6.1 less than 6.2. Okay, next. What do we have? Okay, now you have to compare the temperature of the air trap in the capillary tube. So how to compare the temperature? You can see here no Bunsen burner. The other side got Bunsen burner down there. So how can we compare the temperature? Okay, this is very easy. Yes, very good. You can say again 6.2 greater than 6.1 or vice versa. 6.1 less than 6.2. Okay, so now the next question, name the physical quantity represented by the length of the air trap. Okay, students, what is the physical quantity represented by the length of the air trap? The length of the air trap, it tells us what? It shows what? It tells you what? The length of the air trap. It represents what? Is it temperature? Is it pressure? Is it volume? Or whatever. Represent what? Displacement? No. Thermal equilibrium? No. The length of the air trap represent what? This question relates to gas law. Okay. Pressure, are you sure? The length of the air column represent what? It represent pressure. No, it's not pressure. It represent what? Changes in the height of the column will change what? Will change the volume. Yes, Sinway, the answer is volume. Okay, Nicholas, volume. So the air column represent volume. So here you can see that when temperature increase, volume of the air trap increases. Okay, so the answer is volume. Okay, the physical quantity represented by the length of air trap refers to volume. All right. Okay, next. What is the relationship between the physical quantity we name in B, which is volume and temperature? Okay, how to relate volume and temperature here? I just mentioned it before. How we relate volume and temperature. Yes, you can say that. Temperature increase, volume increase. Temperature higher, volume higher. Or you just write increase, increase. Or you can say directly proportional. Okay, temperature directly proportional to volume. Volume directly proportional to temperature. Yes. Okay, very good. Okay, so now name the physics law involved in this question. Name the physics law involved. So what law we apply here? Which law relates volume and temperature? Nicholas, you sure? Which law relates volume and temperature? Which law? No. Ini Gail Lusek baru belajar tadi. Ini pressure law. Gail Lusek relate pressure and temperature at constant volume. So yes, it's supposed to be Charles' law. Okay. Remember, Boyle's law relate pressure and volume, where pressure inversely proportional to volume at constant temperature. And then we have Charles' law. Charles' law relates volume and temperature, where volume directly proportional to absolute temperature at constant pressure. And then we have Gay-Lussac law or pressure law, relates pressure and temperature, where pressure directly proportional to absolute temperature at constant volume. Okay, so this one relates to Charles' law. Volume increases, temperature increases at constant pressure. Okay, are you clear now, students? Okay, good. Okay, now look at question D. Okay, you see this graph given, a graph of a volume against temperature in degrees Celsius. There is -273 shows there in the graph. So the first question they ask you, what is the name given to the temperature theta? Theta is here. Theta is here at negative 273 degrees Celsius. So what do we call this negative 273 degrees Celsius as? Theta. Okay. What is the name given to the temperature theta, which is at negative 273 degrees Celsius? Yes, we call it as absolute zero. Okay, absolute zero. Yes, very good. Okay, number one, state one characteristic of gas at temperature theta. So state one characteristic of gas at absolute zero. Just now I tell you what happened to the gas molecule at temperature theta. Okay, Okay, sorry student, my laptop is out of battery just now. Okay, sorry for the technical problem. Okay, cikgu lupa nak buka dia punya charger. Okay, so we continue. Alright. Okay, what is the characteristic? One characteristic of the gas at temperature theta. Okay, can you state? Can you state the temperature? I am back, Nicholas. Sorry, tadi battery. My laptop is out of battery. Okay. What happened to the gas molecule at absolute zero? Anyone? Stationary. Okay, can you write it in proper scene way? You can say gas molecules at stationary. Please add in gas molecule there. Okay, gas molecule at stationary. Or you can say, yes, zero volume. Okay, the volume is zero. Okay, the gas molecule is at stationary or the volume of the gas is zero. Okay, we go with the second question. Okay, now we have question 2. You are given, the question is quite long. You can see diagram 8.1. We have 3 diagram there, 8.1, 8.2, 8.3. Diagram 8.1 shows an uncalibrated mercury. Uncalibrated mercury thermometer means there is no scale. Okay, there is no scale in the mercury. Okay, placed in a beaker containing ice cube and water at 0 degrees Celsius, where the length of the mercury column is 6 cm. And diagram 8.2 shows the length of the mercury column L 20 cm when it is boiled until 100 degrees Celsius. And the third diagram shows the length of the mercury column, which is L 16 cm, where the thermometer is now placed in a hot liquid with a temperature theta degree Celsius. So these are the 3 related diagrams. Okay, first, we immerse at 0 degrees Celsius. This is the length, 6K from the bottom here. Okay, and then at 100 degrees Celsius, this is the length of the mercury from this end. And then for the third diagram, we now immerse the thermometer in a hot liquid where we don't know what the temperature is. So we call it as theta. Okay, and it shows the length of 16 cm from the lower level. So what is the question that follow? Okay, first, temperature is based or derived quantity. Okay, this is very easy. It should be base quantity. Students, how many base quantity that we have? Altogether, how many base quantity that we have in physics? They are 7. Yes, they are 7. So I hope you know what are those 7 very well. Okay, now B1, based on diagram 8.1 and 8.2, determine the difference in length of mercury column. Okay, we zoom to diagram 8.1 and 8.2. What is the difference between the length of the mercury column? Okay, what is the difference? So to know the difference, we minus. So 20 minus 6 is 14 cm. Okay, 14 cm. Okay, now next question. Based on diagram 8.3 and your answer in B1, can you determine the temperature of the hot liquid? Okay, can you please find the temperature of the hot liquid? Okay, I want you to try this. Use your calculator according to this diagram 8.1, 8.2, 8.3. Find what is theta. Okay, I'll give you a few seconds, a few minutes to work on this question. How can we determine a reading or a temperature from an uncalibrated thermometer? Okay, which one? Okay, how to do? Okay, try to calculate what is theta. From all these 3 readings you are given in each diagram. Okay, you can determine what is the value of theta. Okay, Nicholas, 71.42. Okay, how about the rest? Can you get 71.42? So how to come out to that answer? So this is the formula that we apply. Okay, this is the formula. Theta is equal to L theta divide L 100 multiplied by 100 degrees Celsius. So where to look? Where is L theta? Where is L 100? Okay, so you can look from here. Okay, you can look from here. So this is the lower part of the mercury where the length is calculated from. So down here at 0 degrees Celsius, the length is 6 cm. Okay, and 100, at 100, the length is 20 cm. And this is theta, where the length is 16 cm from the bottom. So where is L theta calculated from? Between 0 degrees Celsius and theta degrees Celsius, mean the green arrow. So how to find the length of the green arrow? So to find the length of the green arrow, 16 minus 6. Okay, 16 minus 6. So L theta is 10 centimeter. Okay, and then where to look L 100? L 100 is the length between 0 degrees Celsius and 100 degree Celsius. The blue arrow. So how to find the blue arrow? 20 centimeter minus 6 down here. So we'll give you 14. So L theta is 6. L 100 is 14 centimeter. Okay, so it will give you 71.43 degree Celsius. Okay, I hope you're clear with that. Okay, then B3, what will happen to the boiling point of the water when it is boiled on the top of a mountain? Why do you say so? Okay, what happened? The normal boiling point is 100 degrees Celsius, right? So what happened when we boil a water on the top of a mountain? Is it no change? Or is the boiling point increases? Or is the boiling point decreases? And why you say so? So the answer is decreases or less than 100 degrees Celsius. Because what happened up there pressure is lower. Yes, Nicholas. Up there pressure is lower. So when pressure decrease, temperature decrease. So the boiling point will drop less than 100 degree Celsius. Okay. Okay, next question C. Okay, now we are given diagram 8.4. It is a design of thermometer can be used to determine the body temperature of a patient. Okay, and in diagram, in table 8.1, they give you a few choices of thermometer. Okay, they give you thermometer P, Q, R, and S with these three characteristics. This is the range of temperature it can measure. Two options, 0 to 100 or 30 to 45. And then the diameter of the capillary tube, small or big. And then the accuracy, 0.1 or 1 degree Celsius. Ini means it can read up to 1 decimal place. Ini dia baca round number hanya 20, 27, 21. This one, 27.1, 20.5, 23.0, like that. Okay. So what is the question? Based on table 8.1, choose the most suitable range of thermometer. Okay, suitable range of thermometer to measure the body of temperature. So which range will you choose? 0 to 100 or 30 to 45? Which one is a suitable range? Choose the range first. 0 to 100 or 30 to 45? So we choose 30 to 45 degrees Celsius. Why? Why we are choosing this range? Why we are choosing this range? Because, yes, this is normal temperature of human body in between 30 to 40 degrees Celsius. Okay, normal human body temperature. And then number 3, choose the suitable diameter of the capillary tube of the diameter. So capillary tube, want to choose a big capillary or small capillary? Which one is better? Okay, ini yes, normal human body temperature is in between that range of 30 to 45 degrees Celsius. So you no need to choose the range from 0 to 100. Okay, so which one? Small or big capillary tube? Small or big? We choose capillary with a small tube. Why? Because it is more sensitive to temperature change. Okay, so we choose small because it is more sensitive to temperature change. Okay, not big, Nicholas, small. Okay, you can check back from your module or from your workbook about the thermometric properties of thermometer. Okay, question 3, students. I think this is the last question we discussed for today. Then the rest we can continue on the next lesson before we enter a new chapter, wave. Okay. Okay, question 3. Block P and Q in figure 1 have the same mass. Okay, you can see P in black color, Q in white color. They have the same mass. They are immersed in a boiling water for a long time. P and Q are then transferred into beaker X and beaker Y respectively. So P transfer into beaker X and Q transfer into beaker Y. Okay, as you can see in this figure. And this is the information you are given with. The mass of the water in both beaker X and Y is the same at 0.25 kg. Initial temperature of the water in the beaker also the same. So they give you specific heat capacity of P, Q, and also the water respectively as shown here. Okay. So the first question, state the initial temperature of the block. What is the temperature of the block before we transfer them into beaker X and beaker Y? Okay, answer is yes, 100 degrees Celsius, because initially we boil them for a long time. And we transfer into X and Y, so its initial temperature is 100 degrees Celsius. Second, why is the final temperature of the water in beaker Y higher than that in beaker X? So after some times, when we immerse block P of 100 into beaker X, and we immerse block Q also at 100 into beaker Y. So after a few minutes, we find out temperature of water in beaker Y is higher. Why is that so? Why? Our boiling point is 100 degrees Celsius, JAYA. Okay, boiling point is 100 degrees Celsius for water. Okay, unless you put in salt or any other impurities, then it will go beyond 100 degrees Celsius. Yeah, because of the low specific heat capacity. Very good. Okay, because Q has a low or smaller specific heat capacity, which means block Q release heat faster, so the temperature of the water increase faster. Remember, a substance or an object with low specific heat capacity, they absorb heat faster. They also release heat faster. All right. Okay, next. Okay, we have to calculate the rise in temperature of the water in beaker Y if block Q release 1,400 joule of heat energy. Okay, so how to find the temperature rise or the temperature difference? Mean we are looking for theta. So this is the information you are given. Mass of the water 0.25. And this is the specific heat capacity of the water. We are looking for a rise in temperature of the water in beaker Y. Okay, it released this amount of heat Q. So we are using this equation. Q equal mc theta. What is Q? Heat released by block equal to the heat absorbed by the water. mc theta. So 8,400, we do the substitution. And from here, we can find the temperature change or the temperature rise is 8 degrees Celsius. Okay. And B2, what is the assumption we made in this calculation? When you do this calculation, what assumption we made? What is meant by heat released by block equal to the heat absorbed by water? So it shows that there is no heat loss to the surrounding. Okay, this is the assumption we made. There is no heat lost to the surrounding. Okay, I think the final question for today, C. Okay, no heat loss to the surrounding. Yes, very good. Okay, final question for today. Why a dented ping pong ball can be repaired by placing the dented ball in hot water? Name the gas law correspond to this problem. So they ask you to name the gas law, means this situation must refer to a gas law. Okay, which law can you identify? Boyle's law, Charles' law, or pressure law? Why a dented ping pong ball can be repaired by placing the dented ball into hot water? So the answer is temperature increase. When we place into hot water, okay, hot water means temperature increase. And then you can see that the shape of the ball went back to its original shape. So what changes there? Mean the volume. The volume changes. So what law relate volume and temperature? Where temperature increases, volume also increases. So this is to do with Charles' law. Okay, Charles' law. It's Charles' law, not Boyle's law, not exact law. Okay, it is Charles' law. Temperature increase, volume of gas expand. So it is to deal with Charles' law. Okay, gas pressure not gas pressure tak tambah. Okay, volume is the one that changes. You can see the shape change, mean the volume change. Okay, so it is Charles' law. Okay, so if you have any further question, you can PM me in the Telegram group or you can ask from the class group in the Telegram. So I think that's all for today. So if you miss any part of this lesson, you can always watch back to these videos. And for the remaining question, you can try to do them first. And we will continue the discussion by next Tuesday. Okay, so I guess that's all for today. You can get ready for the next lesson. Thank you very much for your cooperation. Thank you very much for your presence. I really appreciate that. Okay. So anything else you are not clear with this lesson, you can always ask me. Okay, from the Telegram. Okay, thank you, students. Okay, thank you, everyone. So I see you again next week. Okay, thank you. Bye bye. Have a great day.